And it cuts off all of these and all of these, all of the descendants. And how much does it cut off? Well, they're d to the L max minus L sub I are in the shadow of the ith code word. So none of these can be code words. Similarly, this casts a shadow. And this casts a big shadow. D to the L max minus L sub 1. Okay? All right, now, these shadows cannot overlap. Otherwise, it wouldn't be a singular code. It wouldn't be a tree code. So, we must have the following. Summation of D of L max minus L sub I, that's the shadow cast by the ith code word, from I equals 1 to m, that's the number of x's takes on, has to be less than or equal to the number of nodes at depth L max, which is D to the L max. Aha. So, the L max cancels, D to the L max, divide both sides, so this is summation of D to the minus Li, less than or equal to 1. So, then depths of the m nodes in this D-array tree have to satisfy this, so that no code word, binary code or D-array code word, is the prefix of another. In fact, let's call this also prefix-free. Prefix-free. So, instantaneous, self-punctuating, tree code, or prefix-free. No code word is the prefix of another. Great. So that's the craft inequality. Now, that allows us to do the optimization. So I look at my notes so we don't waste too much time. Optimal codes. So x goes to C of x. These have length L of x. And we wish to minimize the expected value of L of x, which is equal to summation of P of x times the length of the code word associated with x, which I will write as summation pi L sub I. In other words, I just changed from this notation to subscript notation. So the object is to minimize summation of pi Li subject to summation of D to the minus Li is less than or equal to 1. So it looks interesting and doable. I know right away that if all the p's are equal, I should probably have all the word lengths equal, if possible, or as close to equal as possible. Uniform gives you uniform. But beyond that, it's hard exactly to see what I want to achieve here. So, this is the expected description length of x, and we want to minimize it. So, form J of L equals summation of pi Li plus the Lagrange multiplier associated with summation of d to the minus Li. Now if we minimize this, it's like minimizing this and then plugging in the constraint. So I write this as e to the minus Li log d. That's how, because that's an identity. And it makes it easier to take the derivative with respect to L. All right, dj dli is equal to, all right, let's make it j just because these are dummy indices I. The only term that depends on Lj is the jth, so this is pj here, plus lambda, and again, only the jth term here is active. We take the derivative with respect to Lj, which is minus Lj e to the minus Lj log d. I bet I did that wrong. I think it's minus log d minus log d of this. Okay, the derivative of an exponential. And then, of course, as before, this is d to the minus Lj. I just reconstitute it. And I set that equal to 0. All right. And that's going to give us the answer. Remember, we're trying to solve for the L's, which minimize this functional J of L. So you get d to the minus Lj equals Pj over lambda log d. Now, this sum, Kraft inequality with equality equals 1, that implies this sum equals 1, but summation of Pj equals 1. So that implies 1 over lambda log d equals 1, or lambda equals 1 over log d. And that implies from here that d to the minus Lj is equal to Pj times 1 over log d times log d. Okay? But now we take the logs of both sides, minus Lj equals log to the base d of Pj. Thus, Lj star, the optimal code word length, is log to the base d of 1 over p sub j, where I've used the fact that minus the log is log of the reciprocal. So, great. This is it. These are the code word lengths that satisfy Kraft's inequality and minimize the expected description length. Now there is a problem. These aren't integers. We'll fix that. Right now, let's assume that we can have these non-integer code lengths and see what happens. Then L star, which is summation pi L sub I star, is summation of pi. Now what's L sub I star? Log to the base d of 1 over p sub I. From I equals 1 to m. Aha! This is the entropy in dits or whatever, log to the base d units of x. Now we've also proved if this is the minimum, remember I just showed the first variation is 0, but if it's the minimum, we have shown L, well, the expected value of L of x greater than or equal to the entropy. And this I wanted to call L, the expected length. So, entropy again enters the picture. If I want to assign some symbols x short descriptions and some long, and have them be instantaneously decodable, then the description length should be like the log of the reciprocal of the probabilities, and the expected description length will be the entropy to that base, and no other assignment will give you less. So this is really, except for the fact of the non-integer thing here, this is that doesn't keep the lower bound from being true. So this is the main theorem of data compression. We've already addressed it slightly with the AEP. We say there are roughly 2 to the NH sequences. Let's use NH bits to describe one. The problem with that is there's a certain probability of error that results, and there's an NH plus epsilon. And maybe we can do better than NH plus epsilon. So let's examine a particular code, and then that will be the last thing we do today. And it's called a roof code. I think Shannon discussed it in his 48 paper. let L sub I